So now we have talked about all the necessary components for drawing a state machine diagram. Now let's take a look at this problem statement and try to come up with a state machine diagram for this object section in this ASU course registration system. Now to construct a state machine diagram, you have to ask yourself the following questions. What are the possible states that the class can be in? What determines the states that the class is in? And also to what events does each state respond, and what happens when the events occurs, etc, etc. Okay, so in this state machine diagram for section, we will need an initial state and also a final state. Now we have to think about what are the possible states that we can have within this class section. So for a particular course section, may be either available, so we will have the state called available, or it may be full, right? That means we don't have any seats available within the section. Or eventually the course or the section may be over. After the drop period, if we have enough students in the class, then we're going to over the class. And then finally, if we don't have enough students, then we may cancel. We may cancel the class. So these are the possible states that we can have within the state machine diagram. Then when we construct a section, we're going to go from the initial state to available. And we will set the number of enrolled students to be 0. Because initially we don't have any students in the section. So that's why we initialize the variable to 0. Then according to the problem statement, when we have 40 students in the class, then the class becomes full. So now we may move from available to full, and we have a change event. When enroll is equals to 40, then we're going to move from available to full. Then when the course section is full, we may go back to available. It's possible. And this is going to happen when we drop student. When we call this operation to drop student, then we have to unregister the student. And then we go back to the available state. And then when a course is available, notice that when registration closed, and the number of students that we have within this section is bigger than or equals to 10, then we're going to offer that course section. And then when do we go into cancel? Okay, when registration closed and the number of students that we have within the class is less than 10, then we will cancel the section. And then finally, after we cancel the section, we have to destroy the section. Okay, and this is the state machine diagram that we have for this class section within the ASU course registration system. And now let's say we know exactly what operations that we have within the class. Then we can include more information within the states that we have within this state machine diagram. For example, under the available state, we may add student or we may drop student. And when we add student, we have to register the student. And when we drop student, we have to unregister the student. Okay. And also when we cancel, okay, when we cancel the section, these are the things that we have to do. For example, we have to unregister all the students. And also we have to delete the schedule. And finally, you also have to delete the section itself. And this is the state machine diagram for the section class in the ASU application domain. And it's also possible to have composite state machine diagram. That means it's nested and we have a state machine diagram within another state machine diagram. We may have sequential composite state machine diagram. That means an object is in exactly one state in one of the nested state machine diagrams. Or concurrent composite state machine diagram. That means an object is in exactly one state in each of the regions of the state machine diagrams. And I'm going to show you some examples. So this is an example of sequential composite state machine diagram. And you can see that under this state, we're going to have another state machine diagram. And this icon indicates that this is a composite state. That means within this state, we're going to have another state machine diagram. And this is what we call the superstate, and this is a substate. And we may have transition going from the superstate, a state from the superstate into the boundary of the substate. That means we're going to go into the initial state of the composite state machine diagram. We may also have a transition going out from the substate. That means we're going to exit this composite state machine diagram and then go into a particular state within the superstate. So now using this composite state machine diagram, we can capture the more complicated behavior within this state forward. So what do we mean by having a transition going from the boundary of this forward state to the first gear? That means no matter we are in the first gear, second gear, or third gear, whenever we stop the car, we are going to go back to the first gear. And then we can shift up or shift down and then go to different gear within this forward state. And this is what we mean by composite state machine diagram. So we have one state machine diagram within another state machine diagram. We may also have concurrent composite state machine diagram. Again, this incomplete state, we have an icon here, and this icon denotes that this is a composite state machine diagram. And now you can see that within this incomplete state, we have to do several things at the same time, concurrently, in order to, for example, pass the course. Okay, let's say while you're in this incomplete state, you have to complete all the labs, you have to do the term project, and also you have to take the exam. You have to get all these things done before you can go into the past state. Otherwise, if you cannot get some of them done, then you will fail the course. And this is what we mean by concurrent composite state machine diagram. And notice that in this composite state machine diagram, we have different regions. One region for the lab, another region for term project, and then another region for taking exam. So that means an object will take one of the states within each region. So for example, for the lab part, it's going to be at lab 1. For term project and taking exam, it's going to be at the initial state. And this is what we have talked about in the example. We may have a transition going into the boundary of a composite state or going out from the boundary of a composite state. And it's also possible that we may have transitions that go directly from within a composite state region to an outside region. So that means we go directly from the substate to the superstate. And a transition may have multiple source or target states. And this represents a synchronization or splitting of control. And I'm going to show you an example of a transition that have multiple source and target states. And this is an example of concurrent composite state machine diagram with synchronization. And when we have a bar, then that means we have synchronization. So what do we mean by having a bar with multiple target states? For example, this bar is going to point to A1 and B1 at the same time. This bar actually means that we're going to go into A1 and B1 at exactly the same time. So that means synchronization. And we have a bar here with multiple source states. That means we have an arrow going from A2 and also from B2 at the same time. And again, this means synchronization. That means we have to wait until both A2 and B2 have finished before we go into cleanup. So this bar here just means synchronization. They have to start at the same time and finish at the same time. So now what if we don't have the bar? Then that means we are not doing synchronization. Without synchronization, then that means we will either follow this path or the other path, but not both at the same time. Why? Because a state machine diagram is going to be always deterministic. That means we can always determine the states that a particular. That means we can always determine the states that an object is in at a particular time. And we know that a transition is instantaneous and cannot be interrupted. That means we're going to follow one of the transitions at one time. So that means we're going to follow either this path or the other path, but not both at the same time. So without synchronization, that means we will either go into this path or the other path, but not both at the same time. But using synchronization, it's possible that we're going to go into the two regions at the same time. And that's why here I say that only one of the two transitions will be taken if we don't have synchronization. So some of you may ask, do we have to draw a state machine diagram for every class that we have within the software system? Yes or no? I would say no, because we have so many classes within a software system. If we draw a state machine diagram for every single class that we have within the software system, it's going to take a long time. So that's why here I say that it's not necessary to produce a state machine diagram for every class within the program. But we should draw a state machine diagram for classes with significant dynamic behavior. If the behavior within the object is kind of complicated, then we may have to draw a state machine diagram to clarify the behavior within the object. And that's all I want to cover in this lecture.